Hello all. So my talk will be about Netware Kernel Stack Overflow exploitation. It will mostly be only about Netware Kernel exploitation because there is nothing much to say about Stack Overflow and heap overflow. But the interesting part is about what to do when you have a Stack Overflow. In this case, a remote one, because in the netware world, no one really reversed it before. No one really knows how the kernel works. So the interesting part was to apply all the previous techniques to netware. So quick overview of the talk. Quick introduction about netware. What the OS is all about a debugger for netware. After that, I will present a kernel mode stager, which is a reverse TCP one. And I will present two kernel mode stages, one connect back shellcode and one add user payload. And finally, I will conclude. So this is netware, a beautiful GUI in Java. It's painfully slow. It's almost everything you can say about netware, actually. So why reversing or trying to exploit netware? You could ask yourself, isn't this OS still? Is this OS still alive? Actually, yes, it is. Especially in big corporate networks in the US. I tried to, when I first started working on netware, it was due to a lot of crash reports from the customers. Like when we released the plugin just to detect a service which was absolutely not related to netware. And like one day after that, we have like 20 customers who called us saying all their network system crashed. And the point was, okay, it crashed, but what can we do with that? Another point is no one published anything about reversing in netware, so it was another fun part of the challenge. Another point is I had to reverse everything on the kernel part because there is absolutely nothing, no publication except the NDK, the netware development kit, but it's mostly just for the basic structure, but nothing really low level. And finally, is it possible to apply all previous x86 techniques to netware? So netware, it's kind of modern OS. It's based on x86 CPUs. It has support for multiple processors. Since version 5.0, there is a separation between kernel and userland. It's a bit old, so it's why it can be considered to be modern. There is a support for NX in the user space. And since the latest version, 6.5, it's even compiled with Xen support. So in netware, the equivalent of P and ELF is NLM for netware loadable module. You can find the definition of the NLM format in the netware SDK, the novel netware SDK, yeah. And the file format is fully supported by IDE. So it's a modern OS, but at the same time, it's a bit old because to launch itself, it used a modified version of DOS. So it starts in real mode. DOS launches server.exe. And server.exe creates the full netware user space and kernel space and extract both server.nlm and loader.nlm, which is the core of the netware kernel. When it's done, the CPU is switched in protected mode, and the netware system starts. there are lots of network versions, 4, 5, 6, and 6.5, and multiple service packages. For example, for the latest version 6.5, there are 6 service packs. So the challenge was to make both payload fully generic or generic enough to work on all those versions. However, I did not make them work on 4.0 because it's really too old and everything is different. 5.0, I'm not sure it may work, but the problem is you can't really use a 5.0 system those days because it should crash like for just a port scan. So the good point with Netware is that it's coming with a Kernel Debugger. It's fully integrated in the kernel and in the user space. And all systems and LMs are compiled with debug symbols, so the kernel knows everything about all Netware modules. And to activate the debugger, we have to do left alt, left shift, right shift, and escape. Quick copy of the kernel debugger. You can see all the registers, basic commands. And each time you see one line of disassembly. Useful commands, help, really useful. It's the only way to really know how to use this debugger. And after that, you have, I will just print 5 or 6 basic commands. So cd, it's to change a D word. So it's memory manipulations part. So you have cd or c or cw, which is to change a D word, a byte, or a word. The format is cd, the address, equal, and the value you want to set at this address. Something for dd, which is to dump the value. Another useful command is m. So m is, you use m to search a pattern in the memory. So you have the start address, the size of the blocks you want to search for, and the patterns you are looking for. Last one is b for breakpoint. So it's pretty easy to use. b equal the address you want to set the breakpoint. And after that, you have an optional condition like ex equal 2. You have other commands which is more related to the systems, like .m to find a module in memory, or dm to dump this module. It's useful to find addresses in the systems. You have .g and .i and other related x86 commands. But the problem is there is no command to dump the memory to a file. It was a problem because the kernel core, which are server.nlm and loader.nlm, are not available directly in the system, but they are inside server.exe. So my first approach was to dump them from memory, but it's not possible, so you have to extract them from the exe. So for that, I needed a remote exploit on Netware. So I used the Stack Overflow in the RPC stack. It was in LSA. The RPC stack runs in the kernel space. It took me 1 minute to find it. Problem is, you need a stable return address across all versions of Netware and all service pack. It's not really easy to find. The exploit is actually available in Metasploit. You can find the exploit, the reverse TCP stager, and the shellcode. I will add the add user payload soon. But at this time, this flow is still not fixed, so you still can use it. But if you want, you can find like many other flows in like just 2 minutes. So I present the kernel mode stager, so the reverse TCP one. quick overview, how to resolve the kernel function addresses by finding the debug symbols, how to resolve those symbols, how to migrate the payload, which is useful to not crash the full OS, and how to receive the future stage. So to resolve kernel function addresses, it's useful because we need to create a TCP connection, we need to restore the system, and we need to execute commands. There is no interruption we can use to do that, so we have to know how the kernel works, all the kernel functions. The problem is that Netware, at startup, it destroys the kernel symbols, so we can't find them easily. But the thing is, if you go to the debugger, it is able to resolve those symbols. So we can do it too. So how to do that? By reversing the kernel. So after some time, I found most information, and especially on the debugger. So the debugger is in kernel.nlm, and it stores all the symbols in the hash table debugger symbol hash table. So we need to locate this table in memory, and the way we find this address, it must be generic enough to work everywhere. So the function remove all temp debug symbols is stable across all Netware versions, and it contains a reference to this table. But we have the same problem. Now we know how to find a reference to the hash table, but we need to find the functions which has a reference to this table. To do that, I have 3 different techniques. By using hard-coded address for server.nlm, the problem is all service pack versions will change the address space. It's because all libraries are loaded in memory after each other. So if there is a change in a service pack in one library, all the address space will change. Another solution is to hook the sysenter EIP in the AMSR. It works well, but only in Netware 6.5. But the opposite, not the opposite, but we can also hook the GDT system call gate, and this particular solution works really well on version 6 to 6.5. So the GDT system call hook is like any other ones you can find in x86. So we just get the address in the GDT, and we scan up to find the debugger hash table, and that's it. So after that, we know where the hash table with all the debug symbols is, but we need to parse this hash table to find a particular function we are looking for. To optimize that, the payload only uses function names, but not the module names, because in the kernel space, there is no conflict between 2 function names. So if we look the hash table, it's a chain list of debug symbols with the next element, a pointer to the symbol, a pointer to the name, and a pointer to the module of the symbol. The problem is that the symbol names is actually crypted. It's not really encryption because it's more hash function that is used because the full symbol tables is actually a hash table, and the encryption function is used to improve the hash table. So in the payload, we must directly use the encrypted functions to make the payload smaller as possible. Here you can see the crypt function used by Netware. Pretty easy, just a XOR function. So now that we are able to resolve kernel symbols, we need to find how to migrate the payload to a safer place, because it's a Stack Overflow, and the stack will be erased. So we have to move it somewhere where we can continue. To do that, there is two main techniques. The first technique consists to copy the payload to the GDT, because in Netware there are lots of free spots in the GDT. Another solution is to allocate a new memory and to copy the payload in the memory. I used the second one, not because it's safer, but because it will make everything smaller, especially to receive a new, the next stage. So to allocate the kernel memory, there are lots of functions. It's kind of complex in the kernel itself, but the good thing is there is a lot of wrappers around those functions, like lb malloc. So we just have to use this function to allocate a huge chunk of memory and copy the payload and goes to this memory. After that, to receive the second stage, we need network functions. All network functions in Netware are in tcp.nlm and tcp/ip.nlm. The problem is that those functions are already complex. It's a callback systems, and we could use them, but it would make the payload too big. So we have to find a better solution. And a better solution is actually to find wrappers around those functions. Those wrappers are in BSD sock, which is the BSD equivalent of socket, receive, and send. The problem is those functions are not exported inside the debug hash symbol, but there is another wrapper in libc around the BSD functions, which are itself wrappers around the kernel functions, and we can use the libc reference in the debug symbol hash symbols. Final part of the stages, we have to recover to not crash the whole system. It's often the more complex part, not the more complex, but it's often a not generic part in kernel exploitation. In the case of Netware, I had first to remove a lock on the file system. I'm not sure if it's generic or if it was only related to this exploit, but I had to do it. But a good thing with Netware is to restore the whole system. All we have to do is to call k worker thread, and Netware will do everything for us, restore everything. So now I will present two different kernel mode stages. Basically, most of the time, what we do is we switch back to the user space for common exploitation techniques. But I decided not to do that and to stay in the kernel just for fun. So the first stage is a connect back shellcode. Most common technique to get a shellcode is actually to spawn a new user shell and redirect both the input and output to the socket. The problem with Netware is that actually there is no local user. So there is no shell at all. So how can we get a shell when there is no user and no shell? Thing is, there is no shell, but there is a system console. And this console allows to manage all the Netware system. But it's not a shell, it's a console, it's integrated in the kernel, so there is nothing to interact with the console. There is no file descriptor. Actually, there are file descriptors in the libc, but only in the user space. And we are still in the kernel space. So we need to find something else. Another problem with the console is that it's not a scrollable output, it's a bitmap. So we have to handle it. Like in the payload, we can handle the bitmap and convert it to a kind of scrollable output, or we can do better and create a client that will display a bitmap. I first did that in Metasploit, but it was not generic enough, so I came back to the ugly part, and the payload actually converts the bitmap to a scalable output shell. So reading the console script, after some reversing, I found the kernel functions to do that. By reversing actually the libc wrappers around everything and came back to the kernel, I found most functions to do that. So you have a get system console screen to get the main system ID, get screen size, which returns the screen of the bitmap, the size of the bitmap, sorry, and read screen into buffer to convert the bitmap into readable text. There is no new line inside it, so it has to be handled by the payload too. Writing to the console, like you got your shell, you want to send a command. It's a complex task too. And the solution I use is to inject a key code inside the console by emulating a keystroke. It's the solution, and I think the only one. And the kernel actually provides the function addKey to insert a standard key like A to Z or 1 to 3 to 9 or whatever. Except when you want to send enter, you have to use a special code that I found a reference to this in the kernel. You can find that in the paper if you want. Another problem with emulating a keyboard is that the input buffer is, there is a limit of 32 characters. So the payload has to handle that to send a special character to before each command, so we can send actually long commands if needed. So another thing is, like it's a bitmap, we want to turn it into a scalable output. So we have to know what changed. And for that, I decided to inject a special characters in the screen by using the direct output to screen function. And the new line, I'll talk about that. So the main shellcode loop. Problem is we are still hijacking the kernel loop. So everything we do is actually critical. And we need at the same time to be in our loop and to restore the kernel loop. So there are multiple solutions for that, like moving the kernel loops, the shellcode loop somewhere else. But in my case, I just get lucky. And I found that first solution was when I receive the stage of the commands, sorry, if you directly call receive, it will actually lock the whole system because receive comes back partially in the kernel loop, but still waiting for an event, and this event will never arrive, even if you receive something on the socket, because you are actually locking the whole system, so it cannot detect that something arrives on the socket. So a solution is to use I/O control to know if there is something to read on the socket before do a call to receive. But like we are still in our loop and hijacking the kernel one, we need from time to time to give back the control to the kernel so it can handle everything else, like all the services and the GUI. The solution, actually, Renaud told me that I could try that, so why not? So I tried to use a select call with null arguments. And the good thing is when you do a select call, it gives the full control back to the kernel until the select call returns. So all you have to do in your loop is to add a new select call with null arguments, and it will fully hide the shellcode in the memory. So to resume, the shellcode is we result kernel symbols, we get the screen console information. We do a select to give the control back to the kernel. And at the end of the select, the kernel gives us the control back. We call update screen, which actually detects if the console buffer has changed. If it's the case, we send everything to the socket. After that, we check if there is something to read on the socket. If it's the case, we read it. And we inject all the data in the console screen. And we loop and see if there is anything else to read. So I have a quick demo to actually show you that Netware works. So you can see Netware here. And the exploit to get a console. I hope it will work. It's a bit slow because it's Ruby. Oh, it will work better. If I disable the firewall. Let's try again. Okay. Okay, we got a remote console shell with Netware. So at the prompt, you can try everything you want. Good function, help in the console. Lots of really, really, really useful commands. If you got a Netware console, you will be able to do nothing. So the second part is what can we do? There is something to manage Netware remotely. It's the Netware Remote Manager. It's a web interface. We can do everything with that. And we can even have a console through the web browser. So instead of getting a console that we absolutely don't know how to manage, a better idea would be to inject a new user in Netware and to log on to this web interface to manage the server. So it's the second stage, add user stage. On Unix or Windows, it's pretty easy to do that most of the time. You just use add user, user add, or the net command to create a new user. On Netware, it's really a problem because there is no user at all on Netware. There was in version before 5.0, but since 5.0, there is no more users. So the thing is, there is no local users, but Netware is used to manage E directory. So you have users in the E directory or the LDAP tree. So the thing is, we cannot create local users, but we may be able to add user in the LDAP directory and then manage the system through E directory. So as I said, the payload is just to create a user in the E directory tree. Contrary to the connect batch shellcode, we cannot use the debug symbol hashtable to resolve the functions to manage E directory. And to do that, we need to resolve library function addresses. To resolve them, it's pretty easy. We just have to work inside the module list, which is exported by the kernel. It is stored in internal module list pointer. And as we know how to resolve kernel symbols, we can resolve internal module list. So we know the address of all modules. So once we have the list address, we must check each module of this list and each exported symbol list of each module to find the function we are looking for. And here we need to match both the function and the module name, because you have lots of conflict between names in different modules, like in libc or in BSD. You have the same function name, but it's two different modules. And you want to be sure you are calling the right one. So basically, it's almost the same algorithm than for the kernel symbols, except the hash is split in 2 parts, 2 bytes for the module name and 2 bytes for the function name. Same thing than with the kernel symbols. The module name, the function name is actually encrypted, so we have to use already encrypted hash in the payload. So when we found the right hash for the function name in the symbol list, So we know to find the good functions, and now we have to create a new user. And to create a new user in eDirectory, we must first connect to the eDirectory service, add a new user object, and grant this object supervisor rights to be admin or root, whatever you want. So the step 1, connect to the eDirectory service, it could have been a complicated task. But the thing is, Netware, there is a really cool functions to log in as a server in the eDirectory tree. So if you are locally, you can call these functions to log on in the LDAP services, and you will have full rights on all the LDAP tree. So you don't even have to authenticate to the services locally. The C code to add a supervisor user is quite simple. So you create a Netware eDirectory context. You log in as a server, so no authentication. You allocate a new buffer. You initialize this buffer. In this buffer, you put, it's an object class type. You add a user field. It needs a surname. You can add multiple other information if you want, but you just need those basic fields to add a user. So after that, you add this user object in eDirectory. Now you need to give this user some rights to do something. So you create an SEL, and on the SEL, you give him full supervisor rights to the root 3. And when you have added those rights to this object, you must generate a password for these users. It can be achieved with generate object keeper. It's easy, it's clean, but the problem is those functions, they need access, to a CLib context, which is a kind of libc context, and this CLib context is not available for all threads. And it's actually too complex to add a CLib context directly in the main kernel loop. Because all kernel threads do absolutely not have access to the CLib context. It would have been too easy. So the solution is a kind of injecting in. It's kind of injecting the payload to another process, like if you go to the user space. But in this case, we inject it in a kernel thread, another one, but with a CLib context. To do that, we need to know the structure of a thread. And especially, we have everything here is maybe not the right stuff. It's based on what I reversed in the kernel. So I think it's almost exact, but I can't be sure. So important parts are the wait state flag, stack pointer, the state, and the suspend reason, and the CLib data, which will tell us if the current thread have a CLib context. So we must first resolve the process list address, where we have access to all the thread and all the process. After that, we must walk down in this list to find a thread with the clip context. As I told before, it's the clip data field. And the thread must resume shortly, because if we choose to inject ourselves in a thread and this thread never resume, we will never add a user. So the first things I tried was to get the stack pointer, replace the return address with the return address with the address of the payload, but it was not really a good idea because when your thread is suspended, it will resume not directly in the thread itself, but in the kernel context. And the kernel context will see there is a problem and will lock everything down. So a better solution is actually to rely on the use of Java in mostly, I would say, 50% of the network processes and services. And you can even find kernel drivers that actually use Java. Why Java? Because I'm not sure why, but on Netware, almost all Java processes generate a lot, but really a lot of exceptions. Like if you try to check in 6.5, you put breakpoints on the page fault exception handler, it will never stop. Like it's crazy. So we need to find a thread with a clip context, which is a driver, because all kernel threads don't have clip context. I think, I'm not sure, this is defined by the type attribute in the thread structure. I'm not sure, but I think it's the right definitions. So the idea is to hook the page fault handler, which is interruption 14, in the IDT, and check the current type, and know if we can execute the payload. So it's actually to hook the IDT. So the code stores the current interruption 14 address, replaces it with the payload address, and gives back execution control to the kernel by calling the worker thread function. When a thread generates page fault exceptions, the new interruption 14 handler, which is our payload, is called. Our payload check if the thread, if the current thread has a clip context and is a driver. It's pretty easy to know the current thread with the current thread kernel function. So if the thread is not good, we goes back to the original page fault handler. Else, it's time to restore the original one, execute our previous add user code, and give back control to the interruption 14. So this schema resumes that. Our add user payload is called. We first check there is a clip context in the thread. If it's not the case, we goes back to the original interruption 14. Else, if our thread is a driver, so type 3, we continue. Else, we go back to the original one. So if everything is OK, we first restore the page fault handler. We add a new supervisor user, and we goes back to the original interruption 14. So I'll try to show you a demo. So if we check in Netware, let me check the user first. Recon, OK. So if we try to log on as Recon, it should not work. Okay. Oh, loading. I hope the previous exploit did not. Okay, here we go. So we cannot log on with Recon, so we try the exploit. Here we go. So it should be pretty fast. As I said, with 6.5 to generate a page fault. But with 6.0, it's a bit more slow. So we have to wait like 1 or 2 seconds. But in this case, it will be OK. And now we added a new user, Recon with the password Recon, and this user has full supervisor rights to the e-directory tree. So to conclude, a full kernel exploitation in Netware is not too difficult. It just takes time to understand everything about how the kernel works. In the case of Netware, it's more reliable to exploit everything in the kernel than in the userland, especially due to return addresses, because it's really difficult to find a stable one. What needs to be done? Create a complete framework for exploitation with bind stager and command execution stage. I'm not planning to do it right now. I'm not sure it's really useful. Another fun thing I tried to do, actually, if you remembered, I said that the kernel itself is loaded in memory by using DOS. So the thing is, I tried to create a new stage to actually inject myself in the DOS, which is still in memory somewhere. It's pretty easy to find it. I tried to do that and to, at the same time, change the BIOS code, which can be found in memory too, and then came back in real mode. So we would have been totally hidden from the kernel. It first worked. I was able to do that, go back in real mode. But the problem is when you're in real mode, it's kind of difficult to debug everything. And I stopped at this point. Because I never was able to, after I came back to real mode in DOS and with the BIOS, I never was able to come back in Netware, actually. So that was pretty useless. So that's all, if you have any questions.